We have seen the method of substitution for solving a system of linear equations. The process can be captured as a sequence of elementary operations performed on the system. The process can be quite tedious if done by hand because you have to write down a new system after each operation. But the thing is, for a system of linear equations, the things that really matter are the coefficients of the variables and the right-hand side values. And so we can save a lot of handwriting if we use matrices to capture everything we need to know to solve the system. And here is what we are going to do. We are going to form this matrix here. The first column corresponds to the coefficients of x1, the second column the coefficients of x2, and the third column the coefficients of x3. And the rightmost column corresponds to the right-hand side values, so I can write down 0, 4, minus 2 here. For the first column, the coefficients of x1 are 2, minus 1, and 3. The coefficients of x2 are minus 1, 1, and minus 2. And the coefficients of x3 are 0, minus 2, 1. So the first row of the matrix corresponds to the first equation, the second row to the second equation, and the third row to the third equation. Optionally, we can put a vertical bar separating the coefficients of the variables from the right-hand side values. If we form a matrix that consists of only the coefficients of the variables, we obtain the coefficient matrix of the system. So in this case, the coefficient matrix would be a 3 by 3 matrix. This whole matrix here is called an augmented matrix. The elementary operations for solving a system of linear equations can be translated to a set of operations that we can perform on the augmented matrix, and they are the following. We can multiply a row by a non-zero constant. That means for every number in that row, we multiply it by the same constant. We can add a constant multiple of a row to another row, and we can interchange the positions of two rows. We are going to look at the process of solving our system here in parallel with the elementary row operations that we can apply to this matrix. So this is the system that we are trying to solve, and this is the corresponding augmented matrix. What we are going to do first is to have x1 appear only in the first equation. So we are going to find a way to eliminate x1 from the second equation and the third equation. The first thing we do is we multiply the first equation by a half. The corresponding operation that's applied to the augmented matrix is multiplying the first row by a half, and we write that as R1 indicating row 1. Left arrow means that it is replaced with what comes to the right, 1/2 times row 1. So we have to multiply every entry in the first row by a half. So that gives me 1 minus 1/2, 0, and 0. The next two operations are going to be adding the first equation to the second equation and adding minus 3 times the first equation to the third equation. And the operations on the matrix are replacing row 2 with row 2 plus row 1, and replacing row 3 with row 3 plus minus 3 times row 1, which we can write as minus 3 times row 1. So the first row stays the same. For the second row, I have to add row 1 to row 2. So 1 plus minus 1, that's 0. Minus a half plus 1 is a half. 0 plus minus 2 is minus 2. And 0 plus 4 is 4. For the third row, I have to subtract 3 times row 1 from row 3. So 3 minus 3 is 0. Minus 2 minus 3 times minus half, that's minus a half. And 1 minus 0 is 1. Minus 2 minus 0 is minus 2. Now, if you look at these two equations, they only have x2 and x3. And so I'm going to try to eliminate x2 from the third equation. And I can do that by adding the second equation to the third equation. And that will give me the following system. And the operation on the matrix is replacing row 3 with row 3 plus row 2. So here I have 1/2 plus minus a half, that's 0. And I have here minus 2 plus 1, which is minus 1. And then here I have 4 plus minus 2, that's 2. As you can see, each of the matrices here is the augmented matrix for the system right above it. Now I'm going to continue, but without writing the systems of the equations. I'm just going to perform operations on the augmented matrix. The next thing I'm going to do is multiplying row 3 by -1. Now, if we look at the third row, it represents the equation x3 equals -2. But once we have x3 equals -2, the second equation tells us that x2 has to be 0. And if x2 is 0, the first equation tells us that x1 is 0 as well. So in effect, we can really stop here because we can read off a solution from this. But let's continue. This time, I'm going to add 2 times row 3 to row 2. Now I'm going to add row 2 to row 1. Finally, I'm going to multiply row 2 by 2. If I now write down the system that this matrix represents, it's going to look like this. x1 equals 0, x2 equals 0, and x3 equals -2. This system basically tells us exactly what the solution has to be. If you look at this matrix here, consisting of the columns corresponding to the variables, it has 1s on the diagonal and 0s everywhere else. When you have a square matrix that has 1s on the diagonal and 0s everywhere else, that matrix is called an identity matrix. As you can see, if you have a system that has the identity matrix as the coefficient matrix, then it basically tells you that the right-hand side values will give you a solution to the system. This is rather nice, but we can't always hope to transform every augmented matrix to a form that looks like this. But we can get quite close. We'll see in future videos what we can actually do. I'm going to wrap up with some terminology. Say you have 2 matrices A and B. If one can be obtained from the other via a sequence of elementary row operations, then A and B are said to be row equivalent. So for example here, if I look at the last 2 matrices, these 2, I know that the one down here can be obtained from the one up here by an elementary row operation, but I can also obtain the matrix up here by multiplying the second row of this matrix by a half. Therefore, I can obtain one matrix from the other by an elementary row operation, and so these 2 matrices are row equivalent. In fact, if you pick any 2 matrices shown here, they are row equivalent, and the reason is that elementary row operations are reversible. This is a fact that is not difficult to check. I encourage you to think about that and find out how you can start from this matrix here and go back to the very first matrix here using elementary row operations.